So every now and again I just go ahead and do something silly, and this is one of those experiments. And if you're wondering why the silicon mat is so suspiciously clean in this area, it's because I had to wipe it down with alcohol after starting an electrical fire on it earlier today, because the capacitor, which I thought was mains rated, was not. And it went kapooey. So what we have here is a servo motor. So in other words, it's a permanent magnet rotor brushless DC motor. Now I've got it connected to an AC drive intended for squirrel cage motors. And the question is, will it run? And we often get asked that question. And yes, it does run, but why do we not do it? And let me show you. I've started it up. As you can see, it's shaking. It's drawing more current than it should. And when we look at the current waveform over here, it is not very smooth. I've got my trusty CT over here with a burn resistor connected to the scope. Let's look at that a bit bigger. So there you can see it's all over the place. It's not happy. It does smooth out a bit when you go faster. Let me set my trigger level up a little bit. Manual level. There's a trigger marker over there on the screen. This is 10 milliseconds. And 500 millivolts per division for a scale. So that's about half an amp that I'm measuring, because that's a 1000 to 1 CT. So for every 1 milliamp I'll get 1 millivolt. And over here the current feedback parameter in menu 4 is showing us the same result. In fact, there the current really gone up when I speed it up. It is not happy at all. So yes, they run, but you need to commutate them correctly, and for that you need the Hall effect or an encoder feedback from the motor position, which gives the drive an absolute value of where the shaft position is in degrees, and it knows how to commutate the three-phase rotation in relation to the magnets in the rotor, so that the magnetic field pulls the remains locked to the rotor, and it commutates correctly therefore, and it pushes and pulls correctly. In this case, the drive and the motor are getting out of sync, and it's jumping around and so on. It's not happy about it. So, and also that is a low voltage motor, but even with a high voltage motor I'd have got the same results. It needs a feedback device to a drive which can do servo control or brushless permanent magnet rotor motor control. These days they do have some drives as algorithms which sense the rotor position via the current feedback and are able to control the commutation via that. It's called sensorless control. But in general, with motion applications, you have a feedback device on your motor over there, and the commutation and the position feedback goes back to the drive. It knows where it is. So there's your answer. A brushless motor does, a three-phase motor does run off a induction motor drive, but it's not good. it doesn't work. Actually, it doesn't do any harm, but you're definitely not going to get the performance that you want. It's unfortunately something that doesn't work. We get this question often because I work with these things, and people want to know, can you do it? And sadly the answer is no. There's a practical problem. It does not work. And I'm just seeing more debris from that capacitor from this morning on my desk. It made a mess. There was a nice big black sooty skid mark over there and debris which I had to clean up, and that's one of the benefits of working with a silicon mat, is it doesn't burn and you can clean the mess up afterwards. But one should avoid starting electrical fires on your bench. It's not a good idea. Not good at all. Occasionally you make a mess. You mess up, you do something silly, and a fire is the result. But try not to do it. Don't be like me. Learn from what others do. It was a 63 volt rated cap, and I was trying to connect it to 220, and it didn't end well. Big crater in the side of the cap, and sparks and smoke coming out of it, and debris flying everywhere. What a way to start the day. So I'm going to conclude this talk on our little motor over here that we tried running on a drive. Everybody got to see what happens, and we got to see what the current waveform looks like, courtesy of our CT over here. In fact, we should be able to see the PWM in that. Yes, we can. There's our PWM. Hold. So there you can see the CT is actually catching the drive PWM. And one can see that the commutation is not correct on the waveform over here. It is not happy. So that's why we don't do it. That's why we have the correct type of drive for this type of motor. So what more can I waffle on about? I think not much. I was trying to set up a power factor type demonstration this morning when it went sideways. I put everything away. I thought, okay, can that idea. Let's think of something else to play with. So here we have it. We are playing with the servo motor. I knew what was going to happen, so I'll set up the demonstration and I'll show you guys what happens. And that's it. We're going to wrap it up here, ladies and gentlemen. Thanks for being here. Thanks for watching my videos. Have an awesome day further, and I'll see you sometime for more awesome stuff or stories. Cheers.